All right, we will be continuing on our work with polynomials, and in this video we will be doing some multiplying and factoring with monomials. And I'll start with a brief introduction, a reminder of what monomials are, but mostly we'll do a bunch of examples. Okay, so remember a monomial is a single algebraic term, usually an x raised to a particular power, maybe multiplied by a coefficient. Example might be 5x squared or negative 3x to the fifth. However, in contrast, something like 2x squared minus 5x, that would be a binomial, okay? So in this video, we will be focusing on algebraic expressions that have a monomial as part of them, where maybe we're being multiplying by monomials, or maybe we're factoring out monomials. But we will be applying that multiplication or factoring to both monomials and binomials or trinomials. But all of these will have monomials involved. Sorry, that's quite a mouthful. Okay, so monomials are sort of the theme of the game, the name of the game here. All right, so let's take a look at this first one. We want to do the distributive property with this particular monomial right here, applying it through multiplication to the terms inside the parentheses. Okay, so we will just be distributing, and we need to remember that when we're multiplying terms that have common bases like an x, but with perhaps varying exponents, we would be adding those exponents. So for this first one, I'm going to write out all my work. I don't think your teacher expects you to do that for every single one, but I think on this early one, it's probably good practice. So we have a 4x squared times a negative 5x squared plus a 4x squared times 3x plus a 4x squared times a negative 6. So we did that distributive property, and now we just need to do a whole bunch of simplification. So remember about like terms, our constant terms joined together, we have a negative 20, and then our x terms give us x to the fourth plus a 12x cubed. Recall that this x has a hidden exponent of 1. And then plus a negative 24x squared. Okay, and that would be our final answer right there. And it already is in standard form, decreasing order of exponents. So we've done the distributive property. So that was multiplication. Most of this video, and in fact most of the challenge of this unit, is going in the other direction. It's factoring, okay? So let me try to get something out of the way here and to try to model what exactly we're doing. Okay, so just now we went in that direction from we multiplied, okay? Much of what we will be doing and much of the challenge of this unit is going in the other direction. If I were to give you this expression to have you be able to turn that yellow expression into that orange expression. That's the challenge, factoring, okay? And so in that case, we are pulling out this term by dividing it through each piece and essentially pulling it out front. That's what factoring is. Okay, so that's just a preview of the challenge. One thing that will make your lives a lot easier is if you can easily figure out what the greatest common factor is of a couple terms. So I want to remind you of that. I think you've seen it before, but I want to remind you of that now. So in other words, if we're dealing with these two numbers, 30 and 42, what's the largest number, greatest, that easily goes into, that's what a factor is, both terms. That's what common means, okay? So the largest number that evenly goes into 30 and 42. Okay, so sometimes you can just use your brain and try to think about it. Is it 15, 6? Maybe it's a 6, right? It looks like 6 goes into both. Can we go higher? Maybe, we'll see, okay? But I'm trying to show you that sometimes your brain can lead you astray, and we can't necessarily be perfectly sure. So I have a method that I want to show you, and it involves factoring, prime factorization. So 30 is divisible by 2. That brings it down to 15, which is 3 times 5, okay? So we factored the 30. Let's factor the 42. Always try to divide by 2 first. That brings it down to 21, and 21 is 3 times 7. Okay, so we've broken both terms into their prime factors. Prime means a prime number is a number that can't be divided by any smaller whole number. Its only factors are 1 in itself. And then what terms are common to both? So again, we're looking for common factors. So we have a 2 that's in both, and we have a 3 that's in both. So we will snag those terms, and our greatest common factor is 2 times 3, which is 6. So we kind of got it by guessing early on, but we weren't totally sure about it, but we just went through a process that gets us pretty confident that we have a final answer. So this is called our GCF. 6 is the greatest number that goes evenly into both 30 and 42. Next one, 5x squared. We're going to prime factor that. 5 times x times x. We can factor with variables as well. 7xy is just 7 times x times y. So let's grab factors that are common to both. And there's an x in both. And that's it. Okay, so our GCF is just going to be x. Okay, that's the largest term that evenly goes into both. Next one, this works with larger terms as well. And again, I encourage you to just start dividing by 2 if you can, then try to divide by 3. So 84 divided by 2 brings us down to 42. Divide by 2 brings us down to 21, and that's 3 times 7. And then we have x times x times x. 70x, we could divide by 2. That brings us down to 35, and that's 5 times 7. Whoops. And we just have an x. So we'll just highlight the common terms. Each one has a 2, each one has a 7, and each one has an x. Okay, so our GCF is going to be 2 times 7 is 14x. Okay, that's the greatest term that evenly goes into both. So I just spent a good chunk of time really carefully going through how to get a GCF. I'm not going to go through that process for these next ones. I'm going to assume you've internalized it a little bit, but feel free if I'm going too fast to pause the video and then go through that process for these. So factoring, one thing we try to do first is what I call pull out or factor out a GCF. Okay, so, and put that up front, throw in some parentheses, we're doing the reverse distributive law. So 10x plus 5, GCF is going to be 5. And what stays behind, we have a 2x plus 1. You can always check these by doing the distributive property, okay, and it would check out. Next one, we have a 12x squared plus 3x minus 15. It looks like, well, we want to think about numbers and variables as kind of separate pieces here. There are no variables in this term, so the GCF won't include a variable. So we don't even have to worry about variables for this problem. And it looks like 3 is the largest number that can be pulled out of everything. It turns into 4x squared plus x minus 5. So we're just dividing each of the terms by 3 and writing down the quotient, the result of that division, in the parentheses. That's what sort of stays behind. Okay, so that's our final answer here. Again, another factoring problem. It can get harder, especially when we're dealing with variables. And I can actually see right here that there are no y's in every single term, so I don't need to worry about the y's. But there's an x squared in each term. Okay. Remember, if we were to divide this term by x squared, x cubed divided by x squared does evenly go into it, even though 2 doesn't evenly go into 3. X squared goes into x cubed and leaves an x to the first behind. Okay, so I'm going to pull an x squared out front, and I'm going to throw in my parentheses. I can throw in my plus sign and my minus sign right away. And then let's think about my number terms. I can pull an 8 out front. Okay, so again, we're going to treat numbers and variables as a little bit separate. So we have a 3x to the first that remains behind for the first term, a 2y remaining behind for the second term, and a minus 1. Okay, so we really pulled the entirety of this 8x squared out front. So what stayed behind? A 1, because we want this times the minus 1 to be this term right there. Okay, and I kind of ignored the -1. I just kept it as a subtraction to begin with. All right, so that was a tricky one. You can always check these by doing the distributive property and see if you get what you started with. And honestly, we can sort of go in a circle here. So we can start here, we can factor to come down here, we can distribute to go back up there. We can just keep going forever, okay? But let's not. Let's stop right there.